In the depths of space far beyond our solar system lies one of the strangest planetary systems ever found. A neutron star nicknamed Lich spins like a cosmic lighthouse, and around this dead star several small worlds circle in a storm of radiation and gravity. These were among the first planets ever discovered outside our solar system, and they orbit not a warm sun but a stellar corpse. Today we explore what makes this pulsar system so bizarre, and what it can tell us about how planets survive in the most extreme places. If you enjoy journeys to the edge of what we thought was possible, please like, subscribe and share, and tell us in the comments, what would you ask about planets orbiting a dead star? Thank you for watching. Now let's begin. The Milky Way is a barred spiral galaxy whose stellar disk spans on the order of 100,000 light-years in diameter and contains several 100 billion stars along with gas dust and dark matter distributed in a complex but well-studied structure. The main visible component is a relatively thin disk in which most of the gas and young stars reside, organized into spiral arms and smaller segments that wind around a central bulge of older stars. Above and below this thin disk there is a thicker stellar component with older populations and lower gas content, and beyond that an extended halo of stars, globular clusters and dark matter that surrounds the galaxy and defines much of its gravitational potential. The Sun lies in a minor spiral feature often called the local arm or Orion arm, at a distance of roughly 25 to 30,000 light-years from the galactic center and near the midplane of the thin disk, so that when observers on Earth look out at the sky, they see the Milky Way as a bright band, where lines of sight run through the densest parts of the disk. The sky is divided into constellations which are projected patterns of stars on the celestial sphere, rather than physical groupings, and one of these patterns is Virgo. Virgo marks a direction from the solar system that intersects both stars within the Milky Way and distant galaxies far beyond, but the neutron star known as PSR B1257+12 or Lich lies well within the Milky Way along this line of sight. Measurements of its parallax and of the dispersion of its radio pulses as they travel through the ionized interstellar medium indicate a distance of around 2,000 to 3,000 light-years from the Sun, placing it in the same broad galactic environment as many nearby stars when viewed on the scale of the galaxy. The coordinate system used to describe its position can be expressed in both equatorial coordinates, based on Earth's rotation, and galactic coordinates aligned with the plane and center of the Milky Way. In galactic coordinates, Lich has a latitude of roughly plus 75 degrees, which means it lies far above the midplane of the galactic disk, in a region associated with the thick disk or inner halo rather than the thin disk where most star formation currently occurs. A galactic latitude near 90 degrees would point essentially out of the disk, so a value around 75 degrees corresponds to a sightline that leaves the thin disk and crosses regions with much lower densities of gas and dust. Surveys of neutron stars and other stellar remnants show that many of these compact objects have high space velocities relative to the local standard of rest, acquired either during the supernova explosions that formed them or through later dynamical interactions, and over time these velocities can carry them far above or below the galactic plane. Lich is an example of such a high-latitude object. Its position indicates that it has moved away from the thin disk, where its progenitor star originally formed and now follows an orbit through the galactic potential that takes it through regions of relatively low gas density, on scales of tens to hundreds of parsecs around the neutron star, where a parsec is a unit of distance, equal to a little more than 3 light-years. The local environment is dominated by the general gravitational field of the Milky Way and by a diffuse interstellar medium, rather than by dense molecular clouds or bright star-forming regions. The stellar population in these high-latitude regions tends to be older on average than in the spiral arms, and the mix of stars includes many low-mass main sequence stars, white dwarfs and other remnants that formed earlier in the history of the disk. In models of the Milky Way, the thin disk has a characteristic vertical thickness of a few hundred light-years. The thick disk extends to heights of roughly 1 to 2,000 light-years, and the halo extends farther still. The latitude and distance of Lich place it at a height compatible with membership in this thicker component, rather than in the youngest gas-rich layer. From the standpoint of radio observations, the high galactic latitude of Lich has an important practical consequence. When pulses of radio emission from the neutron star propagate toward Earth, they travel through the ionized component of the interstellar medium, which causes a frequency-dependent delay known as dispersion. The amount of dispersion depends on the integral of the free electron density along the line of sight called the dispersion measure. For Lich, this measure is relatively modest compared with pulsars whose sightlines remain close to the galactic plane, which is consistent with the idea that the path from the neutron star to the solar system passes largely through low-density regions above the main disk. This relatively low dispersion aids in precise timing of the pulses, because the corrections that must be applied for frequency-dependent delays are smaller and can be modelled accurately with current models of the galactic electron density distribution. In addition, the reduced column of gas and dust along the line of sight means that absorption and scattering are less severe than they would be for a similar object viewed through the plane, improving the transparency of the interstellar medium at relevant radio frequencies. On the larger scale of the Milky Way structure, Lich and its planets are part of the overall population of stars and stellar remnants, bound to the galaxy moving in orbits determined by the combined mass of the stellar disk bulge and dark matter halo. The neutron star does not occupy a special location in terms of galactic dynamics, but its high latitude and distance provide useful constraints on its motion when combined with measurements of proper motion and radial velocity. Within the three-dimensional arrangement of the Milky Way, the system sits a few thousand light-years from the Sun in the direction of Virgo, and at a substantial height above the disk in a region where the gas is relatively diffuse and the stellar population is dominated by older stars and compact remnants. In the direction of Virgo, as in other parts of the Milky Way, stars form from cold, dense gas concentrated in molecular clouds that follow the spiral structure of the galactic disk. Within these clouds, gravity gradually overcomes internal support from gas pressure and turbulence in some regions, so that clumps of gas begin to contract and fragment. As a clump collapses, its central density and temperature increase, and a protostar appears still surrounded by an envelope, and often by a rotating disk of gas and dust. Once the temperature and pressure in the core reach values sufficient to sustain stable hydrogen fusion, the object becomes a main sequence star. At this stage, the outward pressure from nuclear fusion balances the inward pull of gravity, and the star can maintain a nearly steady structure for a long period of time. The physical conditions in a molecular cloud, such as its total mass internal motions and metallicity, influence the distribution of stellar masses that emerge. Observations and theoretical models together indicate that most stars form with masses less than or comparable to the mass of the Sun, while a smaller fraction form with significantly higher masses. This distribution is described by the initial mass function, which strongly favors low-mass stars, but still allows a population of more massive objects that are important for feedback and chemical enrichment of the interstellar medium. In the part of the galactic disk that maps onto the Virgo constellation on the sky star formation, proceeds in the same general manner as in other spiral arm segments, with giant molecular clouds giving rise to clusters and associations. Many of the young massive stars formed in these environments reside close to the plane of the disk and remain there for the relatively short durations of their main sequence lifetimes, which for the most massive stars are on the order of only a few million years. The mass of a star at birth largely determines its subsequent evolution. A star with a mass significantly less than that of the Sun consumes its hydrogen fuel slowly and can remain on the main sequence for tens to hundreds of billions of years, far longer than the current age of the universe. A star with a mass similar to that of the Sun evolves on timescales of around 10 billion years, eventually exhausting its core hydrogen, expanding into a red giant and finally shedding its outer layers to leave behind a white dwarf. In contrast, stars with initial masses greater than roughly 8 times the mass of the Sun follow a more rapid and more complex path. After a relatively short main sequence phase, they evolve into luminous supergiants that burn heavier elements in their cores in successive stages. As fusion proceeds to heavier and heavier nuclei, the core structure becomes layered with shells of different elements undergoing nuclear burning around an increasingly compact central region. For the most massive stars that still form neutron stars rather than black holes, this sequence ends when an iron-rich core grows to a mass where it can no longer be supported by electron degeneracy pressure. At that point, the core collapses on a timescale of less than a second, and the outer layers of the star respond to this collapse by accelerating outward in a core collapse supernova explosion. During the explosion, a large fraction of the star's mass is expelled into space at high velocities, carrying newly synthesized heavy elements into the interstellar medium, while the innermost part of the core compresses into a neutron star. In some cases, if the progenitor mass is higher or significant fallback of material occurs, the remnant becomes a black hole instead. The threshold between neutron star formation and black hole formation is not a single, sharply defined value, but studies of stellar evolution and supernova models consistently place the typical progenitor mass that leads to neutron stars in a range starting at about 8 times the solar mass, and extending through several tens of solar masses with details depending on rotation metallicity and mass loss history. The region of the Milky Way that projects into Virgo contains populations of stars at different evolutionary stages that reflect this variety of initial masses and life cycles. Near the plane, one finds star-forming complexes with molecular clouds, young clusters, and short-lived massive stars that are still on or near the main sequence. Over longer timescales, massive stars in such regions end their lives as supernovae and leave behind neutron stars or black holes, while lower mass stars evolve much more slowly and populate the disk and thick disk as older main sequence stars subgiants, giants, and white dwarfs. The material ejected by successive generations of massive stars enriches the surrounding gas with heavier elements, so that new stars forming later in the same broad region start with higher metallicity than their predecessors. Kinematic processes, including the velocities imparted to neutron stars at birth in supernova explosions, and the gradual heating of stellar orbits through interactions with spiral arms and molecular clouds, gradually thicken the vertical distribution of older stars and remnants. As a result, the present-day stellar population along the Virgo line of sight includes young and intermediate age stars near the galactic plane, and older stars and compact remnants at higher latitudes. Over galactic timescales, this cycle of star formation, stellar evolution, and supernova feedback operates continuously, converting gas into stars returning processed material to the interstellar medium and building up the population of stellar remnants. Within this ongoing cycle, massive stars that once formed in spiral arm molecular clouds and evolved through supergiant phases now exist as neutron stars moving through the galactic potential, in various regions including high-latitude environments above the disk that are sampled by sightlines toward constellations such as Virgo. Neutron stars are compact stellar remnants produced when the cores of massive stars collapse at the end of their evolution, leaving behind objects supported mainly by neutron degeneracy pressure and nuclear forces rather than by thermal pressure from ongoing fusion. After a core collapse supernova, most of the outer layers of the star are expelled into space, while the innermost region compresses into a body with a mass typically between about 1 and 2 times the mass of the Sun, and a radius of only around 10 to 15 kilometers. The resulting mean density is comparable with, or greater than, the density of atomic nuclei, so that matter inside a neutron star is in a state that cannot be reproduced in terrestrial laboratories except in very small volumes and for very short times. Simple estimates based on dividing the mass by the volume show that a cubic centimeter of neutron star matter would have a mass of hundreds of millions of tons, and that if the mass of the Earth were compressed to neutron star density, it would fit into a sphere only a few hundred meters across. In the outer layers of a neutron star, the material is thought to form a solid crust, in which atomic nuclei are arranged in a lattice and are immersed in a sea of electrons. Deeper inside, as the density increases above nuclear saturation, density neutrons become the dominant component, with a smaller fraction of protons, electrons, and possibly other particles such as muons. At even higher densities toward the center, the exact composition is not well constrained by current theory and observation. Various models allow for the appearance of more exotic components, including hyperons or deconfined quark matter, but there is not yet a consensus on whether these phases occur in nature. Observational constraints on neutron star masses and radii combined with nuclear physics calculations are used to infer the equation of state of dense matter, which relates pressure and density and determines how compressible the material is. In practice, measurements of masses from binary pulsars and X-ray binaries, and of radii from thermal emission modeling pulse profile, fitting with instruments such as space-based X-ray telescopes and gravitational wave observations from merging neutron star binaries, place limits on the stiffness of the equation of state, and these limits are gradually being tightened as data improve. The strong gravitational field at the surface of a neutron star leads to an escape velocity that is a significant fraction of the speed of light, and the surface gravity exceeds that at the surface of the Earth by factors of hundreds of thousands. Light emitted from the surface is gravitationally redshifted, and photons leaving the star follow curved paths in the surrounding spacetime. In addition to gravity, neutron stars possess intense magnetic fields, often many orders of magnitude stronger than those found on ordinary stars. Typical field strengths inferred from observations of radio pulsars lie around 1 trillion times the magnetic field at the surface of the Earth, and in magnetars the fields can be even higher. The combination of rapid rotation and strong magnetic field in many neutron stars leads to the production of beams of radiation that sweep through space and can be detected as pulsars if the beam crosses the line of sight to the Earth. Charged particles are accelerated along open magnetic field lines near the magnetic poles, emitting radio waves and sometimes higher energy radiation, and the misalignment of the magnetic and rotational axes causes the beam to sweep around as the star spins. Not all neutron stars are observed as pulsars. Some are detected instead as X-ray sources in binary systems, where accretion of matter from a companion star releases gravitational energy that emerges as high-energy radiation. Others are detected through thermal emission at X-ray or optical wavelengths, particularly in relatively young nearby objects whose surfaces are still hot enough to radiate strongly. A growing number of neutron stars have also been identified through their role in gravitational wave events when two such objects merge. The neutron star population in the Milky Way is therefore observed in several different ways, each of which samples different subsets of the underlying distribution. At present, only a few thousand neutron stars are directly observed as radio pulsars or other compact sources, but population synthesis models and simple estimates based on the history of massive star formation suggest that the galaxy contains many more. Typical estimates indicate that the Milky Way may host hundreds of millions to around 1 billion neutron stars in total, most of which are too old, too cool, or too distant to be detected with current instruments. Estimates of neutron star birth rates based on observed and inferred core collapse supernova frequencies are consistent with these numbers and with the age of the galactic disk. These objects are concentrated overall toward the galactic disk, reflecting the sites of their birth in star-forming regions. But they also show a substantial spread in height, above and below the plane, because the supernova explosions that create them can impart high kick velocities. As a result, neutron stars can travel significant distances from their birthplaces over hundreds of millions of years, and populate the thick disk and inner halo as well as the thin disk. A fraction are found in globular clusters where high stellar densities favor the formation of close binaries, and recycled pulsars through stellar interactions. Their spatial distribution is influenced both by the initial distribution of massive stars and by the subsequent motions through the galactic potential. Viewed on galactic scales, neutron stars form a widespread population of compact remnants, each characterized by extreme density, strong gravity, and in many cases rapid rotation and strong magnetic fields. Within this wider population, neutron stars that are observed as millisecond pulsars represent an important subcategory with especially stable rotation, and the object at the center of the Lich system belongs to this group. Such objects are valuable tools for precision timing experiments in many areas of astrophysics. Pulsars are neutron stars that are observed through the arrival of periodic pulses of electromagnetic radiation, most commonly in the radio band, that repeat with a high degree of regularity. Each pulsar is a rapidly rotating, strongly magnetized compact star whose rotation period lies in a broad range from fractions of a second to several seconds, and in some cases down to a few thousandths of a second. The combination of rapid rotation and strong magnetic field creates conditions under which charged particles in the surrounding space are accelerated and produce coherent radio emission in narrow beams that are fixed with respect to the star's magnetic field. The magnetic axis is generally tilted with respect to the rotation axis, so as the neutron star turns, these beams sweep through space. When one of the beams intersects the line of sight to the Earth, an observer detects a sequence of pulses separated by the rotation period of the star. The basic observational signature of a pulsar is therefore a train of pulses with a stable average period that can be measured to high precision. The first pulsars enter astronomy in the late 1960s, when radio observations reveal sources that emit short bursts of radiation at very regular intervals. Subsequent work shows that these objects are not artificial transmitters, but natural astrophysical sources associated with rotating neutron stars. The rotation periods that are measured span much of the accessible range between the breakup limit of a neutron star and the longer timescales allowed by magnetic braking. For typical radio pulsars with periods of a few tenths to a few seconds, the measured period remains stable on short timescales to many significant digits, while over longer intervals the rotation gradually slows down as rotational kinetic energy is converted into particle outflows and electromagnetic radiation. The rate of slowdown is encapsulated in the period derivative, which is usually many orders of magnitude smaller than the period itself. By measuring both the period and its rate of change, astronomers infer characteristic ages, magnetic field strengths, and spin-down energy loss rates, under assumptions that the break-in torque is dominated by magnetic dipole radiation, and that the moment of inertia has a typical neutron star value. In the magnetosphere of a pulsar, the strong magnetic field forces charged particles to move along field lines, and the rapid rotation induces large electric fields that extract particles from the surface or from the surrounding plasma. Near the magnetic poles, open field lines extend outward beyond the light cylinder, the notional cylinder where the corrotation speed would reach the speed of light. In these regions, electric fields accelerate particles to relativistic energies. The combination of curvature radiation inverse Compton scattering and pair production can generate a cascade of particles and photons. Coherent processes in this plasma, although not yet fully understood in detail, are thought to produce the observed radio emission. Higher energy emission at X-ray and gamma-ray frequencies often originates in regions further out in the magnetosphere, such as outer gaps or current sheets, and is observed in many pulsars alongside the radio pulses, or in some cases without detectable radio counterparts. The detailed emission geometry depends on the inclination of the magnetic axis, the structure of the magnetic field, and the distribution of emitting regions so that the observed pulse profile can have one or more components with different shapes and relative intensities. Observationally, pulsars are studied through high time resolution measurements of their flux as a function of time. A radio telescope records a continuous time series, which is then folded at a trial period to build up an average pulse profile with improved signal-to-noise ratio. By adjusting the trial period and, if needed, its derivative, astronomers obtain a stable profile whose features align from one rotation to the next. The times of arrival of pulses are then measured by correlating the observed profile with the standard template yielding precise estimates of the arrival times at the telescope. These times are corrected for effects such as the motion of the Earth around the Sun, the rotation of the Earth, and when necessary relativistic time dilation, in order to refer them to a standard inertial frame associated with the solar system barycenter. Additional corrections remove the frequency-dependent delay caused by dispersion in the ionized interstellar medium based on measurements of the dispersion measure. After these steps, the residual differences between the observed arrival times and those predicted by a simple rotation model encode information about the pulsar's rotation, its motion through space, and any additional influences on the propagation of the pulses. The stability of the pulse train varies among different pulsars. Young pulsars often exhibit timing noise, a form of low-frequency irregularity in their rotation, and may show sudden changes in period known as glitches, which are likely related to internal processes in the neutron star crust and superfluid interior. In contrast, many older pulsars show much smoother spin-down behavior with less timing noise. Among these, a subset with particularly short periods and low period derivatives displays exceptional timing, stability over years to decades, so that the rotation can be modelled as a simple spin-down with very small residuals. For such objects, the pulses function as highly stable rotational clocks. Arrays of stable pulsars are used to construct pulsar timescales that can be compared with terrestrial atomic time standards, and long-term timing campaigns use the correlated perturbations of pulse arrival times across the sky to search for low-frequency gravitational waves. In all cases, the analysis relies on the fact that the underlying rotation is very regular, and that any deviations from a simple model can be detected and interpreted with high sensitivity. Pulsar observations also provide information on the interstellar medium, because the dispersion measure and when polarization is recorded, the rotation measure probe, the integrated electron density and magnetic field, along the line of sight. The scattering of pulses which broadens their profiles and introduces a characteristic frequency dependence gives additional constraints on small-scale density fluctuations in the ionized gas. Over time, changes in these propagation effects can be monitored, allowing detailed studies of the medium between the pulsar and the Earth. For pulsars in binary systems, the periodic modulation of pulse arrival times, due to orbital motion, permits precise determination of orbital parameters, masses, and relativistic effects, such as periastron advance and Shapiro delay, providing strong tests of theories of gravity. In globular clusters and other dense stellar environments, the same techniques reveal complex systems with multiple bodies and exchange interactions. In the broader population of isolated and binary pulsars, the systematic measurement of periods, period derivatives, pulse shapes, spectra, and polarization properties builds up a detailed empirical picture of how rotating neutron stars behave as radio and high-energy sources. Across these diverse applications, the essential observable remains a sequence of pulses whose times of arrival, after careful calibration and correction, provide quantitative information about the rotation of the neutron star, the structure of its magnetosphere, and the medium through which its radiation travels. Millisecond pulsars form a distinct subclass of the pulsar population, characterized by very short rotation periods and relatively low magnetic field strengths, compared with typical radio pulsars. Their rotation periods are generally shorter than about 30,000ths of a second, and can be as low as 1 or 2,000ths of a second in the fastest known cases. In contrast, the bulk of ordinary radio pulsars have periods in the range of tenths of a second to several seconds. The inferred surface magnetic fields of millisecond pulsars obtained from their measured periods and period derivatives under the assumption of magnetic dipole breaking are typically around 100 million to 1 billion times the strength of the Earth's magnetic field, which is lower by about 2 or 3 orders of magnitude than the fields estimated for many slower younger pulsars. These basic differences in period and field strength, together with their often very old characteristic ages, indicate that millisecond pulsars follow a different evolutionary path from the majority of the population. The widely used picture is that most millisecond pulsars are recycled neutron stars that have been spun up through accretion of matter and angular momentum from a binary companion. In this scenario, a neutron star born in a supernova initially appears as an ordinary pulsar with a relatively strong magnetic field and a moderate rotation rate. Over time, its rotation slows as it loses energy. If the neutron star resides in a binary system with a lower mass companion star, the companion eventually evolves and fills its Rochlube transferring gas through an accretion stream or accretion disk onto the neutron star. As matter with angular momentum falls onto the compact object, it exerts a torque that gradually increases the spin rate of the neutron star. The same accretion process can reduce the effective strength of the magnetic field at the surface through mechanisms that are still under study, such as burial of magnetic flux by the accreted material. During the active accretion phase, the system is observed as a low-mass X-ray binary, in which the gravitational potential energy of the accreted gas is released predominantly in X-rays. Observations of such systems, including sources that show coherent X-ray pulsations at millisecond periods, provide direct evidence that neutron stars can be spun up to very short periods by sustained accretion. When the companion star loses most of its envelope, and mass transfer declines or stops, the accretion flow subsides, and the neutron star's magnetosphere expands. At this stage, the neutron star can turn on as a radiomillisecond pulsar, whose rotation has been set by the balance between the spin-up torque during accretion and the spin-down torque from magnetic braking and outflows, the companion is often left as a low-mass white dwarf on a relatively tight orbit, although in some systems the pulsar wind continues to ablate the companion, leading to the black widow and redback families, in which the companion may be strongly stripped or even destroyed over time. Population studies of millisecond pulsars in the galactic field and in globular clusters support the recycling scenario, because their spatial distribution and association with former or current binary companions match expectations for objects that have undergone long periods of mass transfer. The characteristic ages derived from their current periods and period derivatives are often on the order of 1 billion years or more, indicating that they are old neutron stars that have been active for extended intervals. The relatively low magnetic fields inferred for millisecond pulsars are also consistent with the idea that accretion has altered the field configuration, compared with that of young, strongly magnetized pulsars. In addition to this standard scenario, theoretical work has explored other possibilities for producing rapidly rotating low-field neutron stars, including formation channels involving the merger of two white dwarfs or accretion-induced collapse of a white dwarf. In such cases, the neutron star may be born with a high spin rate and moderate magnetic field without requiring a prolonged recycling phase. The relative importance of these channels remains uncertain and likely depends on the environment, such as whether the system forms in the galactic field or in a dense stellar system like a globular cluster. The pulsar at the center of the Lich system, PSRB 1257+12, is a millisecond pulsar with a rotation period of roughly 0.006 of a second. Its very short period and low period derivative place it firmly within the millisecond pulsar region of the period-period derivative diagram, and its characteristic age is estimated to be at least on the order of 1 billion years. Its magnetic field strength inferred from timing measurements lies in the lower range typical for millisecond pulsars rather than in the range of younger radio pulsars. These properties show that Lich is an old, rapidly rotating neutron star whose present rotation rate cannot be explained by simple spin down from an initially fast newborn pulsar without some additional process. For many millisecond pulsars, the additional process is the recycling mechanism described above, and for Lich. Several formation scenarios have been proposed that are consistent with its status as a recycled or otherwise rapidly rotating low-field neutron star. One possibility is that it passed through a low-mass X-ray binary phase with a companion that subsequently evolved into a white dwarf or was disrupted, during which accretion spun up the neutron star and reduced its magnetic field before the present planetary system emerged. Another possibility based on modelling of its spin and field is that the neutron star formed directly with properties similar to those observed today, perhaps through the merger of two white dwarfs, or through accretion-induced collapse followed by the formation of a debris disk from which the planets assembled. Current observations of Lich, including its timing behaviour and its environment, do not uniquely distinguish between these channels, but all viable models must explain how an old neutron star in the galactic field achieves a 6 millisecond rotation period, a relatively low magnetic field, and a stable long-term timing behaviour suitable for the detection of small perturbations caused by orbiting planets. Lich shares the typical spin and field properties of the broader millisecond pulsar population, and its planetary system makes it an informative example for studies of the evolution of recycled neutron stars and their surroundings. The pulsar now known as Lich is first identified as a radio source during targeted searches for rapidly rotating neutron stars using large single-dish radio telescopes. In these surveys, astronomers point the telescope at selected regions of the sky for intervals of many minutes and record the incoming radio signal as a function of time and frequency with high time resolution. The recorded data are then processed to search for periodic signals over a wide range of trial dispersion measures, which correct for the frequency-dependent delay introduced by free electrons in the interstellar medium. For each assumed dispersion measure, the data are de-dispersed and subjected to a Fourier analysis to identify narrow peaks in the power spectrum that would indicate a stable periodicity. In the early 1990s, one such survey conducted with the 305-meter Arecibo radio telescope yields a source whose signal stands out clearly in these diagnostic plots. The signal shows a strong, highly regular periodicity at a period of about 6,000ths of a second, which is much shorter than the periods of most previously known radio pulsars, and places the object immediately in the millisecond pulsar category. Follow-up observations confirm that the signal repeats with the same period, and that its dispersion behavior is consistent with a compact galactic source rather than terrestrial interference. The object receives the designation PSR B1257+12, following the standard naming convention that uses its sky position in an earlier coordinate system. Later catalogues also list it as PSR J1300+1240 when positions are expressed in a more modern reference frame. The measured dispersion measure combined with models of the distribution of free electrons in the galaxy gives an estimated distance of several hundred parsecs, corresponding to around 2,000 light-years, and the direction on the sky places the source within the boundaries of the constellation Virgo. Timing analysis, which refines the pulse period by folding many successive rotations and fitting a model to the pulse arrival times, shows that the rotation period is stable at a value of about 6.2 milliseconds, and that the rate of change of the period is extremely small. These properties indicate that the neutron star is old, and that its rotational energy loss rate is moderate compared with the younger, slower pulsars with stronger magnetic fields. The localization of the source on the sky improves as more timing data are accumulated. By measuring how the apparent arrival times of pulses vary as the Earth orbits the Sun, astronomers determine the position of the pulsar on the celestial sphere with high precision, because any error in position causes a characteristic annual pattern in the timing residuals. Corrections to the assumed coordinates are applied until this pattern is minimized, yielding an accurate right ascension and declination that fix the pulsar's location in the direction of Virgo. Independent measurements using interferometric techniques further constrain the position, and in some cases the proper motion, which describes how the pulsar drifts across the sky, due to its motion through the galactic gravitational field. Once the basic timing solution is established, including the pulse period, its derivative, and the astrometric parameters, the pulsar is incorporated into catalogues of known neutron stars and becomes a candidate for more detailed study because of its very short period and apparently isolated nature. Continued monitoring of PSR B1257+12 with Arecibo and other facilities reveals that although the basic rotation is extremely stable, the pulse arrival times show small systematic departures from a simple spin-down model. When the times of arrival are plotted as residuals relative to the best-fitting rotation model, they do not scatter randomly around zero within the measurement uncertainties, but instead show variations with characteristic timescales of tens to hundreds of days. Detailed analysis demonstrates that these variations have a periodic structure that can be described by the reflex motion of the pulsar around a common center of mass with additional bodies. The simplest interpretation is that one or more objects with planetary masses orbit the neutron star, causing its position to shift slightly as they move. This shift alters the light travel time from the pulsar to the Earth, advancing or delaying the pulses by very small amounts that can nevertheless be measured because the intrinsic pulse train is so regular. In the initial reports, 2 such companions are inferred from the timing data, with nearly circular orbits and orbital periods of roughly 2 and 3 months. The companion masses derived under reasonable assumptions about orbital inclination are of the same order as the mass of the Earth, which is a striking result because they are the first confirmed planets detected outside the solar system. Later refinements of the timing solution add evidence for a third lower mass companion on a closer orbit, strengthening the view that the neutron star is surrounded by a compact planetary system rather than by a single isolated planet. The methodology used in these studies relies entirely on radio timing and does not require direct detection of light from the companions, which would be impossible with current instruments given the faintness and compactness of the system. Instead, all information about the companions comes from how they modulate the precise clock provided by the pulsar's rotation. The discovery is subjected to careful scrutiny because previous claims of planets around pulsars has been withdrawn after improved analysis revealed that apparent signals were due to instrumental or propagation effects. In the case of PSRB 1257+12, extensive observations at multiple frequencies and independent analyses by different groups confirm that the observed timing variations are consistent with orbital motion and cannot be explained by changes in the interstellar medium or by intrinsic timing noise of the pulsar. Over the following years, repeated timing campaigns refine the orbital parameters, improve estimates of the companion masses, and test the dynamical interactions among the companions, which provide an additional independent check on the planetary interpretation. As evidence accumulates, the system becomes widely recognized as the first robustly confirmed example of planets orbiting a star other than the Sun, and the first known example of planets around a neutron star. In subsequent decades, as more exoplanets are found around ordinary stars using radial velocity and transit techniques, PSRB 1257+12 remains distinctive because of its very different host and its discovery method based on timing. In 2015, an international naming campaign assigns the proper name Lich to the pulsar and mythologically themed names to its 3 known planets. But in scientific work, the original designations remain in common use because they map directly onto the history of the discovery and the timing analyses. Within the catalogue of pulsars, Lich is therefore identified both by its coordinate-based names and by its status as the archetype of a pulsar planetary system whose existence is established through precise measurements of pulse arrival times. For the purposes of interpreting its planetary system and radiation environment, the pulsar Lich can be treated as a neutron star with mass and radius in the range established for similar compact objects, even though its own mass and radius are not yet measured with the same precision as in a few benchmark systems. Studies of neutron star formation and observations of many pulsars in binaries show that most neutron stars have masses clustered around a value somewhat greater than the mass of the Sun, with a typical range extending from about 1 to about 2 solar masses. Only a minority of objects are known to reach substantially higher masses. For millisecond pulsars that are not in close edge on relativistic binaries, direct dynamical mass measurements are difficult, so analyses often adopt a mass near 1.5 times the solar mass as a representative value when modelling their structure and surroundings. For Lich, this approach is reasonable. Its spin period, spin down rate, and overall behaviour are consistent with a standard millisecond pulsar, and there is no observational indication that it is unusually massive or unusually light. The radius of a neutron star is set by the balance between gravity and the pressure of dense matter in its interior, and is therefore linked to the equation of state that relates pressure to density at supranuclear densities. Observations of a small number of neutron stars, including measurements that combine X-ray pulse, profile modelling, and gravitational wave data from neutron star mergers indicate that stars with masses around 1.5 solar masses have radii of roughly 10 to around 13 kilometers. These inferences favor an equation of state that is neither extremely stiff nor extremely soft, which would produce much larger or much smaller radii. Although Lich has not been the target of such detailed radius measurements, it is reasonable to assume a radius in this general interval when describing its gravitational field and surface environment. With a mass of order 1.5 solar masses compressed into a sphere only about 10 kilometers across the surface, gravity is several 100,000 times stronger than that at the surface of the Earth, and the escape speed is a significant fraction of the speed of light. Light emitted from near the surface is gravitationally redshifted, and trajectories of photons are bent sufficiently that a distant observer can in principle see regions of the surface that would be hidden on a less compact object. The structure of Lich can be described in layers from the outermost atmosphere down to the inner core. At the top is a very thin atmosphere, only centimeters to meters deep, composed of ionized material whose exact chemical composition depends on the star's history of accretion and particle bombardment. Beneath this is an envelope that helps to regulate how heat from the interior escapes into space, and below that a solid crust that extends for about 1 to 2 kilometers in depth. In the outer crust, atomic nuclei with large mass numbers form a lattice immersed in a sea of relativistic electrons. As depth and density increase, neutrons begin to leak out of the nuclei, forming an inner crust where neutron-rich nuclei coexist with a gas of unbound neutrons. At densities approaching and exceeding the density of atomic nuclei, the distinction between nuclei and free neutrons breaks down. The material enters the outer core, which in many models consists mainly of neutrons, with a smaller fraction of protons, electrons and muons. At these densities, the neutrons and protons are expected to form superfluid and superconducting phases that influence the star's rotational dynamics and magnetic field evolution. Deeper still in the inner core, the density reaches values at which current theories cannot unambiguously predict the composition. Proposed possibilities include matter-containing hyperons, which are baryons with strange quark content, or deconfined quark matter, in which individual nucleons lose their identity. Observational constraints from neutron star masses and radii already rule out equations of state that would collapse such stars too easily, or produce radii that are inconsistent with data, but more than one class of models remains viable. For Lich, as for most millisecond pulsars, there is therefore no direct measurement of its internal composition. Instead, the interior is modelled using representative equations of state that satisfy the ensemble of constraints from other neutron stars under the assumption that neutron stars share broadly similar microphysics. Thermal evolution provides complementary information. A newly formed neutron star is initially very hot, but cools over time through neutrino emission from the interior and photon emission from the surface. For an object with an age of at least several 100 million years, as indicated for Lich by its characteristic age, the internal temperature has declined substantially compared with the early stages, and the surface temperature is expected to be in a range that corresponds to soft X-ray or extreme ultraviolet emission. Direct measurement of Lich's surface temperature is challenging because its emission at these wavelengths is faint compared with its non-thermal magnetospheric radiation, and because it lies at a distance of a few thousand light years, but the likely temperature range can be estimated by comparing with other old millisecond pulsars whose thermal components have been detected. In most practical applications, including the study of its planetary system, the key parameters of interest are the mass radius and resulting gravitational potential at the location of the orbits. For planets at distances of a few tenths of the Earth-Sun distance, the gravitational field of Lich can be approximated using Newtonian gravity, with corrections from general relativity being small on orbital scales, even though they are important close to the neutron star surface. The compactness of Lich expressed as the ratio of its Schwarzschild radius to its actual radius is high, compared with ordinary stars, but similar to that of other neutron stars in the same mass range, which means that generic properties of neutron star spacetimes can be applied. In summary, while Lich does not yet have individually measured mass and radius with narrow uncertainties, all available evidence indicates that it is a typical millisecond neutron star with a mass around 1.5 times that of the Sun, a radius of order 10 to around 13 kilometers, and an interior structure governed by the same dense matter physics that is constrained through observations of other neutron stars. These parameters define the gravitational and physical conditions under which its magnetic field operates, and under which its planetary system exists. The rotation and magnetic field of Lich define the properties of its pulses and the conditions in its immediate surroundings. Timing observations show that the pulsar rotates once every about 6.2 thousandths of a second, corresponding to roughly 160 rotations per second. The rotation period is measured by folding long sequences of radio data until a stable pulse profile emerges, and then refining the period so that successive pulses align in phase over many hours of observation. The value of the period is determined to many significant digits, and repeated measurements over years show that it changes only very slowly with time. The period derivative, which quantifies the rate at which the rotation gradually slows, is of order 10 to the minus 19 seconds per second, a value typical of old millisecond pulsars. From the combination of period and period derivative under the assumption that the spin-down torque is dominated by magnetic dipole radiation, one infers a surface dipole magnetic field, strength of order 10 to the 8 Gauss, and a characteristic age of at least hundreds of millions to a few billions of years. These derived values place Lich among the recycled millisecond pulsars with relatively low magnetic fields and very stable rotation rather than among young high-field pulsars. The spin-down power, which is the rate at which rotational kinetic energy is lost, is then estimated to be in the range usually found for millisecond pulsars high enough to support a magnetosphere filled with relativistic particles but modest compared with the most energetic young pulsars. Radio pulse profiles of Lich measured at frequencies near 1.4 GHz show a single dominant component with a width of roughly 2/3 of a millisecond at half maximum intensity, and about 1 4/10 of a millisecond at 1/10 of maximum. Given the 6.2 millisecond period, this corresponds to a duty cycle of more than 10%, meaning that the emission is present over a significant fraction of the rotation. The average flux density at this frequency is only a few millijanskis, so Lich is a relatively faint radio source, but the high duty cycle and stable profile allow efficient use of gating and folding techniques to improve the signal-to-noise ratio in interferometric observations and timing campaigns. The stability of the average pulse profile over time indicates that the geometry of the emission region and the large-scale magnetic field configuration remain effectively constant on observational timescales. The magnetic field of Lich, treated as a dipole anchored in the neutron star, defines a light cylinder at a radius where co-rotation would reach the speed of light. For the measured rotation period, this light cylinder has a radius of order a few hundred kilometers far larger than the stellar radius, but still small compared with the orbital distances of the planets. Inside this radius field, lines that close within the magnetosphere form regions of trapped plasma, while open field lines emerging from the magnetic polar caps extend beyond the light cylinder and carry a relativistic wind of particles. The inclination between the magnetic axis and the rotation axis is not directly measured for Lich, but the presence of a single broad radio component is consistent with the line of sight that cuts through a substantial portion of the emission region, associated with one magnetic pole or with overlapping emission from two poles in some geometries. The radio emission mechanism in Lich is not special compared with other millisecond pulsars. It is interpreted within the same framework of coherent processes in a magnetized pair plasma, even though the detailed microphysics remains under study. Polarization measurements, where available, provide information on the orientation of the magnetic field lines in the emission region and help constrain the geometry of the system through fits of the position angle swing as a function of pulse phase. But for Lich, the main quantitative constraints on the magnetosphere come from timing and flux data, rather than from detailed polarimetric modeling. At higher energies, Lich is detected as a faint X-ray source. Observations with an X-ray observatory record a small number of photons in the soft X-ray band, over exposures of tens of kiloseconds, and fits to the spectrum show that the emission can be modelled either as non-thermal radiation with a steep power law or as thermal emission from small hot regions on the surface, such as polar caps heated by returning particles. The inferred X-ray luminosity is on the order of a few times 10 to the 29 ergs per second for plausible distances, and the ratio of this luminosity to the spin-down power is lower than that of many other millisecond pulsars. Possible explanations discussed in the literature include an unfavorable orientation of the X-ray beam relative to the observer asymmetry between the two polar caps, or partial absorption of X-rays by matter in the immediate environment, such as residual debris from the formation of the planetary system. Regardless of the detailed origin of the X-rays, the observations confirm that Lich converts only a small fraction of its rotational energy loss into detectable high-energy emission. The combination of low period derivative, low inferred magnetic field, and low X-ray efficiency emphasizes that Lich is an old, relatively low-field millisecond pulsar in which the magnetosphere operates in a stable, low dissipation regime. As a consequence, the pulses provide an exceptionally regular timing reference. When pulse arrival times are corrected for dispersion for the motion of the Earth and for relativistic effects, the remaining residuals relative to a simple spin-down model are small enough that additional influences such as the orbital motion induced by the planets can be measured as variations at the level of microseconds over many years. It is this combination of rapid rotation, precisely known period-low magnetic field, and stable magnetospheric emission that allows the planetary system around Lich to be detected and characterized using pulsar timing. The magnetosphere of Lich is the region around the neutron star in which the electromagnetic field and the associated plasma are controlled primarily by the rotating magnetic field rather than by the surrounding interstellar medium. Close to the star, the magnetic field can be approximated as a dipole anchored in the solid crust, with a surface strength of roughly 10 to the 8 Gauss, inferred from the measured rotation period and its very small rate of change. The rapid spin of about 6,000ths of a second establishes a light cylinder at a radius of a few hundred kilometers, where rigid co-rotation with the star would require matter to move at the speed of light. Inside this radius, plasma is forced by the strong magnetic field and induced electric fields to move approximately with the stellar rotation. The charge density required to enforce this co-rotation is often described using the Goldreich-Julian formulation, in which the rotation and magnetic field together imply a characteristic sign and magnitude of charge density at each position. Deviations from this ideal density produce parallel electric fields along magnetic field lines, which in turn accelerate particles to high energies. Near the magnetic polar regions, field lines that remain open to large distances allow charged particles to escape, and on these open lines the accelerating electric field can be strong enough to pull charges from the stellar surface or from the ambient plasma. The accelerated particles emit high-energy photons through curvature radiation and inverse Compton scattering. Some of these photons interact with the strong magnetic field or with other photons to produce electron-positron pairs, initiating cascades that fill the magnetosphere with a dense relativistic pair plasma. As a result, the inner magnetosphere is not a vacuum but a dynamic medium in which electric currents flow along and across field lines, modifying the nominal dipole structure, especially near the light cylinder. In Lich, the relatively low magnetic field and modest spin-down power, compared with younger pulsars, imply that the magnetosphere operates in a stable low-noise regime, but the basic structure with closed field line regions, open polar caps and accelerating gaps still applies. On magnetic field lines that close well inside the light cylinder, plasma remains trapped and co-rotates with the star, forming a closed zone in which currents complete circuits between the stellar surface and higher altitudes. In contrast, on open field lines that extend beyond the light cylinder, the plasma cannot remain in rigid rotation, and a relativistic pulsar wind is launched. This wind consists mainly of electron-positron pairs and electromagnetic energy flowing outward at speeds close to that of light. As the flow propagates away from the star, it evolves from being dominated by Poynting flux, where the energy resides mainly in the electromagnetic field, to a regime where kinetic energy of the particles becomes important, although the detailed conversion between these components is still an active area of research. For pulsars with very high spin-down power, the interaction of this wind with the surrounding medium produces bright pulsar wind nebulae bounded by a termination shock. In the case of Lich, the total spin-down power is lower and no extended nebula has been securely detected, but the same basic process is expected to operate on smaller luminosity scales, so that a relativistic particle wind still fills the space around the neutron star and carries energy outward. The high-energy radiation from Lich reflects these magnetospheric conditions. Observations with an X-ray observatory detect a faint source at the pulsar position. With an X-ray luminosity of order 10 to the 29 ergs per second, in the soft band assuming a distance of a few hundred parsecs to a few thousand light-years. The spectrum can be described either by non-thermal emission from the magnetosphere represented by a steep power law, or by thermal emission from small hot regions on the surface, such as polar caps heated by backflowing particles from the open field line regions, or by a combination of these components. The inferred X-ray luminosity is a very small fraction of the rotational energy loss rate, consistent with the general trend that old millisecond pulsars convert only a small part of their spin-down power into observable X-rays. Nevertheless, the X-ray detection confirms that energetic particles in the magnetosphere deposit some of their energy in the surface layers and emit high-energy photons that escape into space. At distances beyond the light cylinder, the pulsar wind establishes an environment in which the energy density in particles and magnetic fields declines with the square of the distance from the star. On scales much larger than the light cylinder, but still well inside a fraction of an astronomical unit, the flow remains highly supersonic, relative to the ambient medium, so that any solid or gaseous object in this region is immersed in a continuous flux of relativistic particles and low-frequency electromagnetic waves. This flux can erode or ionize exposed surfaces, modify any pre-existing atmosphere, and generate secondary emission through interactions with surrounding material. Farther out, where the pulsar wind eventually meets the interstellar medium, a termination shock can form, but that radius is expected to lie well beyond the zone where the known bodies in the Lich system orbit, so that their local environment is shaped mainly by the freely expanding wind rather than by shocked material. In addition to particles and X-rays, the radio beam itself contributes to the radiation environment. While the average radio flux at Earth is only at the level of a few millijanskis, the intrinsic brightness temperature of the coherent radio emission is extremely high, and the beam passes repeatedly through any region that lies within its angular pattern. However, the total energy carried by the radio band is a tiny fraction of the spin-down power, so its direct dynamical effect on surrounding matter is negligible compared with that of the particle wind and higher energy photons. The combined picture for Lich is therefore that of a compact neutron star whose rotating magnetic field maintains a filled magnetosphere out to the light cylinder, launches a relativistic electron-positron wind on open field lines, and produces non-thermal and possibly thermal X-ray emission from magnetospheric processes and heated polar caps. The strengths of the magnetic field and spin-down power set the overall energy scale, while the 6 millisecond spin period sets the size of the light cylinder and the characteristic timescale of electromagnetic variations in the immediate surroundings. Any material orbiting within this environment experiences a steady exposure to relativistic particles, X-rays, and the structured electromagnetic field produced by the rotating magnetized star, and these conditions define the physical background against which the architecture and properties of the Lich planetary system must be understood. Pulsar timing uses the regular sequence of pulses from a rotating neutron star as a timing reference to detect and measure small changes in the star's motion, including those caused by orbiting planets. For Lich, as for other millisecond pulsars, radio observations produce time series of the received signal at one or several frequencies sampled at intervals much shorter than the rotation period. These data are divided into segments, and each segment is folded at the known spin period to build an average pulse profile with high signal-to-noise ratio. By comparing this profile with a stable template, the time of arrival of each integrated pulse is measured to a precision that can be significantly better than a microsecond under favourable conditions. The sequence of pulse arrival times at the telescope is then transformed from the local clock to an international time standard and corrected for the motion and gravitational field of the Earth, so that each timestamp is referred to the solar system barycenter. Additional corrections account for the dispersive delay introduced by the ionized interstellar medium using the measured dispersion measure and a model of its frequency dependence. After these steps, the resulting times of arrival represent the emission events at the pulsar as they would be recorded by an ideal observer at rest at the barycenter of the solar system and observing at effectively infinite radio frequency. A timing model is then fitted to these barycentric arrival times. The simplest model includes the rotation frequency of the pulsar and its time derivatives, the pulsar's position on the sky, its proper motion, and where measurable its parallax. The parameters are adjusted so that the model predicts the arrival time of each pulse as closely as possible. The difference between each observed arrival time and the corresponding model prediction is called a timing residual. If the model includes all relevant physical effects, these residuals cluster around zero with amplitudes consistent with measurement uncertainties and intrinsic noise. If additional physical processes are present but not yet included in the model, the residuals display systematic patterns as functions of time. For an isolated pulsar with a simple spin-down behavior, a model that includes position spin frequency, and a small number of frequency derivatives is usually sufficient. In contrast, if the pulsar moves in an orbit around a common center of mass with one or more companions, its distance to the solar system barycenter changes periodically as it moves toward and away from the observer. This changing path length introduces a varying light travel time, which advances or delays the arrival of pulses by small amounts that repeat with each orbit. In timing residuals, a single circular orbit produces a sinusoidal pattern with a period equal to the orbital period and an amplitude directly related to the projected size of the pulsar's orbit along the line of sight. From this amplitude and period, and with an assumption about the pulsar mass, one obtains the mass function of the companion, which sets the minimum companion mass consistent with the data for an unknown orbital inclination. An eccentric orbit produces a more complex but still predictable pattern that can be described by the standard set of Keplerian orbital parameters. When more than one companion is present, the timing residuals contain a superposition of several periodic signals. In practice, the timing model for a system like Lich is extended to include one Keplerian orbit for each suspected planet. Fitting this model to the data yields for each companion an orbital period, a time of periastron passage or equivalent phase parameter, an eccentricity, an argument of periastron, and a projected semi-major axis for the pulsar's motion. Together with an assumed pulsar mass, these parameters give minimum masses for the companions and their orbital separations measured in astronomical units. The quality of the fit is judged by how much the inclusion of the orbital terms reduces the timing residuals and by whether the residuals remaining after the fit are consistent with noise. For Lich, long-term observations with the Arecibo telescope and other instruments show that a model with only spin-down parameters leaves residuals that vary systematically with characteristic timescales of several tens and several hundreds of days. Introducing a single orbital companion improves the fit but still leaves significant structure in the residuals. Adding a second companion with a different orbital period removes most of this structure and yields minimum masses for two planets of a few Earth masses each on orbits with periods of roughly 2 and 3 months. Subsequent timing campaigns with a longer time baseline and improved instrumentation detect additional lower amplitude residuals on a timescale of a few tens of days, which can be modelled as the effect of a third, much lower mass companion on a closer orbit. The resulting timing solution shows that 3 companions on nearly circular orbits account for the observed residuals over many years and across multiple radio frequencies, supporting the interpretation of the system as a compact planetary system. The precision of millisecond pulsar timing is such that changes in arrival times much smaller than a microsecond can in principle be detected over long baselines, but in practice the timing precision is limited by a combination of radiometer, noise, pulse phase, jitter, and variations in the interstellar medium. For Lich, the achieved timing precision is sufficient to measure the reflex motion, due to companions with masses of order, the Earth at orbital distances comparable with those of the inner planets of the solar system. Because pulsar timing measures only the radial component of the pulsar's motion, the orbital inclinations and true companion masses remain uncertain in a purely Keplerian fit. However, in a system with more than one planet, mutual gravitational perturbations introduce small secular changes in the orbits that cause deviations from simple Keplerian motion. In the Lich system, such interactions between the 2 more massive planets produce detectable non-Keplerian contributions to the timing residuals. By modelling these interactions with an n-body dynamical model, astronomers constrain the orbital inclinations and therefore determine the true masses of the planets, not just the minimum values. This analysis shows that the 2 outer companions have masses of a few Earth masses and that their orbits are close to but not exactly in a simple mean motion resonance. In the broader context of exoplanet detection, methods pulsar timing is distinct in that it does not rely on measuring changes in stellar spectra or small dips in stellar brightness, but instead exploits the rotational stability of the neutron star as a timing reference. It is most effective for rapidly rotating old millisecond pulsars with low timing noise, because their pulses can be predicted with high accuracy over many years. The method is sensitive to low-mass planets at small orbital distances and can provide accurate measurements of orbital parameters and, in favorable cases, true planetary masses. Its main limitation is that only a small fraction of pulsars have both the required timing stability and observational coverage, so the number of known pulsar planetary systems remains small. Lich is the best studied example, and the quantitative description of its planetary system rests entirely on the application of this timing technique to its stable sequence of radio pulses. The planetary system around Lich consists of 3 confirmed planets on compact, nearly circular orbits at distances that are small compared with those of the terrestrial planets in the solar system. Timing analyses show that all 3 companions complete their orbits in periods of a few tens to a few hundreds of days, and that their masses are in the range from a small fraction of the mass of the Earth up to a few times the mass of the Earth. The planets are commonly referred to as Draugr, Poltergeist, and Phobetor in the naming scheme adopted by the International Astronomical Union, and in pulsar timing work they are designated as the innermost, middle, and outermost companions of PSRB 1257+12. The orbital separation of each planet from the neutron star is described by its semi-major axis. For this system, the semi-major axes lie at distances of a few tenths of the Earth-Sun distance, the quantity known as 1 astronomical unit. Under standard assumptions for the mass of the neutron star, the innermost planet orbits at a distance of roughly 1/5 of an astronomical unit, the middle planet at a distance of roughly 1/3 of an astronomical unit, and the outer planet at a distance slightly below 1/2 of an astronomical unit. At these separations, the orbital periods inferred from Kepler's laws and confirmed by timing data are on the order of a few tens of days for the innermost planet and a few months for the middle and outer planets. The orbits are nearly but not exactly circular, with eccentricities that are small enough that variations in distance from Lich during each orbit remain modest. This configuration means that the 3 planets occupy a compact region around the neutron star comparable in size to the region inside the orbit of Mercury, if transplanted into the solar system, but populated by bodies whose masses and dynamical relationships differ from those of Mercury, Venus, and Earth. The masses of the planets are constrained by the amplitudes of the timing variations and by dynamical modelling of their mutual perturbations. For planetary companions detected via pulsar timing, the raw mass information appears as a minimum mass that depends on the unknown inclination of the orbital plane relative to the line of sight. In the case of Lich, the gravitational interactions between the 2 more massive outer planets have been measured and modelled in detail, allowing their true masses and inclinations to be estimated rather than only minimum values. The results indicate that the middle and outer planets have masses of a few times the mass of the Earth, placing them in the category of super-Earths or high-mass terrestrial-type planets in terms of bulk mass, while the innermost planet has a mass that is only a small fraction of the Earth's mass, comparable with or somewhat larger than the mass of the Moon. Together, these 3 masses represent a small fraction of the total mass of the system, with the neutron star dominating the gravitational potential, but they are large enough to produce measurable effects on the pulsar's motion and on each other's orbits. The spacing between the planetary orbits is such that the ratio of orbital periods between the middle and outer planets is close to a simple rational number which has implications for their long-term dynamical behavior that are examined through numerical integration of the equations of motion. The planetary orbits are approximately coplanar, as required by the success of a single set of inclination angles in reproducing the timing variations over many years, although small mutual inclinations cannot be excluded within current uncertainties. No additional planets with masses comparable to or larger than those of the three known companions are detected at orbital distances similar to or within a factor of a few of those measured, because such bodies would generate timing signals that exceed the measured residuals once the three-planet model is included. This does not rule out the presence of much lower mass bodies such as asteroidal fragments or dwarf planet-sized objects, because their influence on the pulsar's motion would be below the current sensitivity of timing observations, but it does imply that the dominant architecture of the system consists of these three planets on closely packed low eccentricity orbits. From the perspective of orbital dynamics, the architecture of the Lich system is notable for having planets of roughly Earth-like mass and lower, located at distances where the gravitational field of the neutron star is strong, and where the circumstellar environment is defined by a relativistic particle wind and high-energy radiation, rather than by a relatively quiescent stellar wind and optical radiation as in the solar system. Nevertheless, the orbital parameters themselves can be described using the same Keplerian framework that applies to planets around ordinary stars. The orbital velocities at the measured semi-major axes are of order tens of kilometers per second, comparable with those of inner solar system planets, and the orbital angular momenta of the planets constitute only a small part of the total angular momentum budget, which is dominated by the spin of the neutron star. Long-term numerical integrations that use the measured masses and orbital elements show that the orbits are stable over timescales comparable with or longer than the characteristic age of the pulsar, provided that the mutual inclinations remain small and that no additional massive companions are present on intersecting orbits. In these simulations, the planets exchange small amounts of angular momentum that lead to slow, quasi-periodic variations in eccentricities and longitudes of periastron, but the semi-major axes remain bounded and the system does not experience close encounters or orbit crossing. The absence of large, rapidly growing instabilities in these models is consistent with the persistence of the timing signatures over the decades since the system was first monitored. The architecture inferred from present data is therefore that of a compact three-planet system in which an innermost low-mass planet orbits closest to Lich on a short-period orbit, flanked by two more massive planets on wider, nearly circular orbits, with periods of order 2 and 3 months all orbiting well inside one astronomical unit from the neutron star. This geometric and dynamical structure sets the stage for more detailed consideration of how the planet's composition, surface conditions and interactions with the pulsar environment may have developed within this compact configuration. The two more massive planets in the Lich system occupy orbits whose periods are close to a simple ratio, and this near commensurability has important consequences for the long-term dynamics and for the extraction of planetary masses from timing data. The orbital period of the middle planet is on the order of 2 months, while that of the outer planet is on the order of 3 months. The ratio of these values is near 3 to 2, so that for every 3 orbits of the middle planet, the outer planet completes roughly 2 orbits. This configuration resembles a mean motion resonance in which the orbital frequencies of 2 bodies satisfy a simple integer relation. In an exact resonance, the gravitational interaction between the planets at specific orbital phases can lead to libration of certain combinations of orbital angles and to characteristic patterns in the evolution of eccentricities and longitudes of periastron. In the Lich system, detailed dynamical modelling based on the timing data indicates that the planets lie close to but not exactly within such a resonance. The small deviation from exact commensurability and the finite eccentricities lead to slow secular variations in the orbital elements of both planets. These variations are detectable in the pulsar timing residuals as departures from strictly Keplerian motion, because the changing gravitational perturbations modify the pulsar's reflex motion over timescales longer than a single orbit. By fitting n-body models that include mutual gravitational interactions, it is possible to reproduce the timing data over many years with a set of planetary masses and orbital elements that are consistent both with the observed near commensurability and with long-term dynamical stability. The dynamical fits show that the two outer planets have masses of a few Earth masses each, with orbital inclinations that are neither exactly face-on nor edge-on relative to the line of sight. The innermost much lower mass planet exerts only weak perturbations on the outer pair, so its gravitational effect on the long-term dynamics is limited, and its presence does not disrupt the near-resonant relationship between the middle and outer planets. Stability analyses integrate the equations of motion for the pulsar and planets over timescales up to hundreds of millions of years using the best-fitting masses and orbital parameters as initial conditions. These integrations account for the mutual gravitational forces among the planets and between each planet and the neutron star, but neglect additional effects such as general relativistic precession and tides, which are small on the relevant scales. The results show that for a broad range of initial conditions consistent with the timing data, the system remains stable, the semi-major axes of the planets undergo only small oscillations, eccentricities remain modest, and there are no episodes of close encounters or orbit crossing. The near 3:2 ratio of orbital periods between the two outer planets plays a role in maintaining this stability by constraining the phase relationships at which gravitational perturbations accumulate. If the planets were moved significantly away from this near commensurability, while keeping the same masses and separations, some configurations would become less stable on long time scales, illustrating that the observed architecture occupies a region of parameter space that is favorable to long-term survival. In addition to confirming that the present system is dynamically robust, the modelling sets upper and lower limits on possible additional planets. A massive fourth planet on an orbit between or just outside the known ones would in many configurations drive the system toward instability over long integrations, or introduce timing signals that are not observed. The absence of such large unexplained timing residuals and the need for long-term stability therefore argue against the presence of additional planets with masses comparable to or exceeding those of the two outer companions at separations similar to theirs. Smaller bodies such as asteroid-sized objects or dwarf planet-sized fragments could exist without violating present constraints, because their gravitational effects would be too small to detect and would not strongly modify the overall stability. The question of how the Lich planets formed is less well constrained than their current dynamical state. The environment around a neutron star formed in a core collapse supernova is initially hostile to the survival of any pre-existing planets from the progenitor system. The explosion expels a large fraction of the stellar envelope, alters the gravitational potential, and can impart a velocity kick to the remnant. The intense photon and particle flux during the supernova and the subsequent early pulsar phase would strongly heat and ablate any nearby planets. For this reason, most formation models for pulsar planets around Lich and similar systems propose that the planets formed after the supernova event from material that accumulated in a disk around the neutron star. Several disk formation channels have been discussed in the literature. One possibility is that a companion star, perhaps a low-mass main sequence star or a white dwarf, transferred mass to the neutron star for an extended period and was eventually disrupted, leaving behind a disk of gas and debris from which planets condensed. Another possibility is that fallback material from the supernova itself, which did not reach escape velocity, settled into a disk at small radii and later cooled and fragmented. In each scenario, the neutron star is surrounded at least temporarily by a dense rotating disk whose mass may range from a small fraction of a solar mass down to much lower values. The disk cools by radiating energy and by transporting angular momentum outward through viscous processes or instabilities. As it cools, solid particles can condense, and if the disk retains enough mass and remains present long enough, these solids can aggregate into larger bodies. The characteristic timescales for planet formation in such disks, based on scaling from protoplanetary disk models and on order of magnitude estimates of viscous evolution, are on the order of millions of years, which are short compared with the characteristic age of Lich. One of the constraints any formation scenario must satisfy is that the total mass of solids in the disk and the efficiency of planet formation are sufficient to produce planets with masses of a few Earth masses within the compact region observed. Another constraint is that the resulting planetary orbits must emerge from the disk with low eccentricities, and must either be stable from the outset or evolve into a stable state through migration and damping of eccentricities. The near commensurability of the outer planets suggests that convergent migration within the disk could have played a role with the planets forming at different radii, and then moving inward or outward until trapped into a configuration close to a mean motion resonance. However, because the properties of disks around neutron stars are not as well constrained observationally as those of disks around young stars, and because the high-energy environment may alter standard planet formation pathways, models of pulsar planet formation remain uncertain in their details. For the Lich system, the observed planetary mass's compact architecture and stable, near-resonant configuration are consistent with formation from a post-supernova or post-mass transfer disk, followed by a period of orbital evolution that established the present arrangement. The available data do not uniquely distinguish between different disk origins, and there is no direct observational evidence for the former disk itself. As a result, the formation models for the system remain plausible scenarios constrained by current timing and dynamical information rather than definitive reconstructions. What is firmly established is that whatever its origin, the planetary system has achieved a configuration that is dynamically stable over long timescales, and that exhibits subtle orbital relationships that can be measured through precise pulsar timing. The innermost planet in the Lich system, Draugr, is a low-mass terrestrial body on a short-period orbit that circles very close to the neutron star compared with the scale of planetary orbits in the solar system. In Pulsar timing catalogues, it is listed as PSR B1257 plus 12b, or PSR B1257 plus 12a, and in the naming scheme adopted by the International Astronomical Union, it is called Draugr. Its presence is established through its contribution to the timing variations of Lich, which appear as a low-amplitude short-period signal superposed on the larger effects of the two more massive outer planets. The timing solution that includes this inner companion yields an orbital period of about 25 1/4 days and a semi-major axis of about 0.19 astronomical unit, placing Draugr well inside the orbit of the innermost planet of the solar system would have if it were placed around Lich. The orbit is consistent with being essentially circular within current uncertainties, with an eccentricity compatible with 0 in most fits, and the inclination inferred from dynamical modelling is around 50 degrees relative to the plane of the sky. These parameters indicate that the planet follows a nearly circular path at a nearly fixed distance from the neutron star, with an orbital velocity of order tens of kilometers per second, set by the gravitational field of a neutron star with mass around 1.5 times the mass of the Sun. Because the orbital period is only a few tens of days, and the planet is small, and likely solid tidal forces raised by Lich are expected to have synchronized its rotation with its orbital motion on timescales much shorter than the age of the system, so that Draugr probably keeps the same hemisphere facing the neutron star in a tidally locked state, although the exact rotational state cannot be measured directly. The mass of Draugr estimated from timing data and dynamical interactions with the outer planets is about 2/100ths of the mass of the Earth, which is roughly twice the mass of the Moon. This makes Draugr one of the lowest mass exoplanets, with a well-determined mass and the least massive of the 3 planets in the Lich system. Its mean radius inferred from interior models that relate mass and radius for rocky compositions is about 1/3 of the Earth radius. Combining this radius with the mass yields a surface gravity that is about 1/5 that of the Earth, so that a person standing on such a world, if it were possible to do so, would weigh much less than on Earth, although this illustrative comparison does not correspond to any current observational capability. The implied bulk density depends on the assumed composition, but is broadly consistent with a predominantly rocky body with a mixture of silicate minerals and possibly metallic components, rather than a volatile rich ice world or a mini gas giant. However, the radius estimate is model dependent and is not measured directly, so the exact internal structure remains uncertain. Within the framework of these models, Draugr can be described as a sub-Earth mass, sub-Earth radius planet, whose mass and size place it in a regime similar to that of large solar system moons, but orbiting a neutron star instead of a main sequence star. The energy environment at the orbit of Draugr is controlled by the output of Lich, in both electromagnetic radiation and relativistic particles. Observations with an X-ray observatory show that Lich has an X-ray luminosity in the band from about 0.3 to around 8 kilo electron volts, of a few times 10 to the 29 ergs per second, which can be modelled either as non-thermal emission from magnetospheric processes, or as thermal emission from small hot regions on the neutron star surface, such as polar caps heated by returning particles. At a distance of roughly 0.19 astronomical unit, this X-ray luminosity translates into an incident X-ray flux on the order of hundreds to thousands of times the X-ray flux received at the top of Earth's atmosphere, although the exact value depends on the detailed spectral shape and beaming pattern of the emission. In addition to X-rays, the spin down of the pulsar releases rotational energy at a rate of roughly 10 to the 35 ergs per second, in the form of a relativistic particle wind and low-frequency electromagnetic waves. Only a small fraction of this spin-down power intercepts the cross-sectional area of Draugr, but the particles that do reach the planet carry enough energy to erode or modify exposed surface material and to contribute to the heating and ionization of any atmosphere or exosphere that might be present. Models of atmospheric escape and irradiation for planets around neutron stars treat both the X-ray flux and the pulsar wind as drivers of atmospheric loss. These models show that for planets to retain substantial atmospheres over timescales of hundreds of millions to billions of years at distances of a few tenths of an astronomical unit, their masses generally need to be comparable to or larger than the mass of the Earth, so that their surface gravity can hold onto gas that is heated and ionized by high-energy input. For bodies with masses much lower than the Earth mass, such as Draugr, with only a few % of the Earth mass, the escape of light gases is efficient, and the time required to remove a thick atmosphere is shorter than the age of typical millisecond pulsars, unless additional protective factors such as very strong planetary magnetic fields or unusually low wind fluxes are present. Because the wind properties of Lich and any intrinsic magnetic field of Draugr are not measured directly, the detailed atmospheric history of Draugr cannot be reconstructed, but the combination of low-mass modest surface gravity and strong high-energy environment makes a long-lived dense atmosphere unlikely in current models. In thermal terms, the simplest estimate of the equilibrium temperature of Draugr treats the planet as a body that absorbs incident radiation and re-emits it as thermal radiation according to its temperature and albedo. Under this assumption, and with a representative luminosity for Lich, the equilibrium temperature of Draugr is of order a few hundred degrees above absolute zero, with values near 260 to about 300 Kelvin often quoted. This range overlaps the black-body temperatures of inner solar system planets, but the comparison is incomplete because Lich emits a larger fraction of its radiation at high photon energies than the Sun does, and because non-radiative energy deposition by the particle wind can modify surface and atmospheric temperatures. In addition, if Draugr lacks a substantial atmosphere, local surface temperatures would vary strongly between the hemisphere facing the neutron star and the hemisphere in permanent night, and between illuminated and shadowed regions, and would be set by a balance between direct irradiation conduction into the subsurface and re-radiation into space. No direct observations currently constrain these temperature distributions, and the equilibrium temperature values derived from simple models should be regarded as indicative rather than as precise surface conditions. The geological state of Draugr is unknown. For a small, likely rocky planet of this mass internal heat, sources include residual heat from formation radiogenic decay of long-lived isotopes and any tidal heating produced by small departures from a perfectly circular, perfectly synchronized orbit. The measured eccentricity is very small, and the present tidal heating rate is therefore expected to be modest. Over long times, the interior would cool and may transition from a partially molten to a largely solid state, with any early geological activity declining. The bombardment of the surface by relativistic particles and high-energy photons can produce a regolith layer through impact processing and sputtering, in which atoms and molecules are knocked out of the uppermost layers of rock, altered chemically, and sometimes redeposited in nearby regions. If any volatiles such as water ice or carbon-bearing compounds were present initially, they would be vulnerable to destruction or removal under continued exposure to this environment, except perhaps in deeply buried layers or in permanently shadowed regions where direct irradiation is limited. Searches for thermal infrared emission from dust in the Lich system with a space-based infrared observatory have not detected bright debris, which places limits on the amount of small warm dust grains in the system, but does not exclude the presence of larger asteroidal bodies or more massive planets. For Draugr, these observations imply that it does not sit in the middle of a dense, optically thick dust disk at present, and that its immediate surroundings are relatively clear of small dust that would irradiate strongly in the infrared. Overall, the picture that emerges from current data and models is that Draugr is a very low-mass, compact, probably rocky planet on a nearly circular, tidally locked orbit, at about 1/5 of an astronomical unit from Lich, immersed in a radiation and particle environment dominated by the neutron star's spin-down power and X-ray emission. Its mass and proximity to the pulsar make it a useful probe of how small solid bodies behave and survive in such extreme conditions, but its detailed surface appearance, internal structure, and any residual atmosphere remain beyond the direct reach of present observations, and must be inferred from general physical arguments applied to its measured orbit and bulk properties. The middle planet in the Lich system Poltergeist is a super-Earth mass body on an intermediate orbit between the inner low-mass planet and the outer planet. In Pulsar timing catalogues it is designated PSR B1257 plus 12 C or PSR B1257 plus 12b, and in the naming scheme adopted by the International Astronomical Union, it is called Poltergeist. Timing solutions give an orbital period of about 66½ days, and a semi-major axis of about 0.36 astronomical unit, so Poltergeist orbits Lich at a distance a little under 2/5 of the Earth-Sun separation. The eccentricity of the orbit is small, with values close to 0.02 in detailed fits, so that the distance from the neutron star varies only slightly over each revolution. The inclination relative to the plane of the sky is around 50 degrees, consistent with the value required by dynamical modelling of the timing data. At this distance, and for a neutron star mass near 1.5 times the solar mass, the orbital velocity is of order tens of kilometers per second, and the gravitational potential is still strongly dominated by Lich. The orbital plane is approximately aligned with that of the inner and outer planets, forming a nearly coplanar compact configuration. The mass of Poltergeist is derived from the amplitude of the pulsar's reflex motion, and from the mutual perturbations between Poltergeist and the outer planet that appear in the timing residuals. When these non-Keplerian effects are modelled with an n-body code, the inclination and true mass of each planet can be inferred rather than only a minimum mass. For Poltergeist, the resulting mass is about 4 3/10 times the mass of the Earth, with uncertainties at the level of a few tenths of an Earth mass. This value places Poltergeist firmly in the super-Earth regime. Interior structure models that relate mass and radius for rocky and partially volatile rich compositions yield an estimated radius for Poltergeist of roughly 1 9/10 times the radius of the Earth, consistent with values compiled in exoplanet catalogues. Combining this radius with the mass gives a mean bulk density moderately higher than that of water, and comparable with values for rocky or rock-dominated planets rather than gas-rich mini-Neptunes. However, the radius is model-dependent and not measured directly, so the exact fraction of iron, silicates and volatiles in the interior remains uncertain. Within the range allowed by current models, Poltergeist can be described as a compact super-Earth, whose mass and likely radius suggest a predominantly solid interior that is differentiated into a denser core and a silicate mantle, with any low-density volatile component limited in mass compared with the bulk rock. The orbital period and small eccentricity imply that tidal effects between Lich and Poltergeist have had ample time to act over the characteristic age of the system. Tidal torques tend to drive the rotation of the planet toward a state of synchronous rotation, in which the same hemisphere faces the neutron star, and they tend to damp eccentricity. For a planet of several Earth masses at a distance of about 0.36 astronomical unit order of magnitude estimates indicate that tidal locking can be achieved on timescales much shorter than billions of years if the initial eccentricity and rotational state are not extreme. The very small eccentricity measured today is consistent with efficient tidal damping. Under these circumstances, it is likely that Poltergeist rotates with a period equal or close to its orbital period, so that one hemisphere receives continuous illumination from Lich, while the opposite hemisphere remains in permanent night, although this rotational state cannot be measured directly. The strength of tidal heating in the interior depends on the current eccentricity and on the planet's internal dissipation parameters. Given the low eccentricity, present-day tidal heating is expected to be modest compared with the radiogenic heat generated by long-lived radioactive isotopes, but it may contribute to maintaining partial internal convection, and in combination with the higher mass could prolong geological activity relative to a lower mass body at similar age. The radiation and particle environment at the orbit of Poltergeist follows from the measured and inferred emission of Lich. X-ray observations show that Lich has a soft X-ray luminosity of order a few times 10 to the 29 ergs per second. At a distance of 0.36 astronomical unit, this corresponds to an incident X-ray flux roughly an order of magnitude lower than that at the orbit of Draugr, but still significantly higher than the X-ray flux received by terrestrial planets in typical main sequence systems. In addition to X-rays, the pulsar releases rotational energy at a rate of about 10 to the 35 ergs per second as a relativistic particle wind and low-frequency electromagnetic radiation. Only a small fraction of this spin-down power is intercepted by the geometric cross-section of Poltergeist, but the particles that reach the planet have relativistic energies and can sputter material from the surface, ionize any atmospheric gas, and generate secondary particle cascades. The total energy flux from the pulsar wind at 0.36 astronomical unit depends on the wind's angular distribution and composition, which are not measured directly for Lich, so estimates rely on generic pulsar wind models. Studies of neutron star planets that apply such models indicate that for a planet of several Earth masses at orbital distances of a few tenths of an astronomical unit, the combined effect of high-energy photons and pulsar wind particles can remove light atmospheric components such as hydrogen and helium efficiently over time scales shorter than the age of the system. For heavier molecules and for atmospheres initially dominated by heavier gases, the outcome depends on the balance between gravitational binding, magnetic shielding, and the history of high-energy irradiation. In the case of Poltergeist, the higher surface gravity compared with Draugr makes atmospheric retention more favourable, but the strong and long-lasting high-energy input still acts against the survival of a thick Earth like volatile, rich atmosphere. No direct observations of any atmosphere around Poltergeist exist, and there is no current capability to detect atmospheric signatures for planets in pulsar systems. The thermal state of the planet's surface and near-surface layers can be approximated by an equilibrium temperature derived from the total luminosity of Lich and the orbital distance. For Poltergeist estimates in exoplanet catalogues give a characteristic equilibrium temperature of around 190 Kelvin, under the assumption of a simple black-body balance and a specified albedo. This temperature is lower than the mean surface temperature of the Earth, and comparable with temperatures at which volatiles such as water would be frozen in the absence of significant greenhouse heating. However, these equilibrium values do not include the spectral hardness of the incident flux, or the contribution of the pulsar wind, and they do not account for possible greenhouse layers or other atmospheric processes. If Poltergeist lacks a substantial atmosphere, the actual surface temperatures would span a wide range between permanently illuminated and permanently dark regions, as well as between low and high latitude areas, and would depend strongly on local albedo thermal inertia and topography. If a thin or moderate atmosphere is present, horizontal heat transport could reduce temperature contrasts, but would be subject to continuous ionization and erosion by high-energy particles. Without direct data, these possibilities remain model-based. The geological structure of Poltergeist is not accessible to observation, but its mass and likely radius suggest an internal composition that can be explored with existing models for super-Earth interiors. For masses of about 4 Earth masses and radii near twice the Earth radius, solutions that match the bulk density generally involve an iron-rich core containing a significant fraction of the mass surrounded by a silicate mantle of substantial thickness. Depending on the initial inventory of volatiles and the subsequent history of irradiation, and escape a residual volatile layer in the form of high-pressure ices, or a thin fluid or gaseous envelope may or may not be present. The interior temperature profile is set by residual heat from formation radiogenic heating and any tidal heating. Over billions of years, these heat sources can maintain convective motions in the mantle of a massive terrestrial planet, possibly supporting a long-lived internal dynamo if enough conducting fluid is present in the core, although the effect of the intense external magnetic field and particle environment on such a dynamo is not well understood. At present, these aspects of Poltergeist's interior remain theoretical. Infrared observations of the Lich system have not detected bright excess emission from warm dust, which suggests that Poltergeist does not reside in a dense warm debris disk. This supports the view that the current orbital environment is relatively free of small dust and gas, and that the planet's interaction with its surroundings is dominated by the pulsar's radiation and wind, rather than by collisions with a massive population of small solids. Within the limits set by timing data and by current models, Poltergeist is thus characterized as a super-Earth mass planet on a low eccentricity intermediate orbit at about 0.36 astronomical unit from Lich, with a likely predominantly rocky interior enhanced surface gravity relative to the Earth and continuous exposure to a high-energy environment produced by the millisecond pulsar. Its well-measured mass orbital parameters and role in the near-commensurate configuration with the outer planet make it a central component of the Lich planetary system and a key example for studying super-Earths around compact stellar remnants. The outer planet in the Lich system, Phobetor, is a super-Earth mass companion on the widest known orbit among the 3 planets, and defines the outer boundary of the compact Pulsar planetary system detected so far. In Pulsar timing catalogues it is listed as PSR B1257+12D or PSR B1257+12C, and in the naming scheme adopted by the International Astronomical Union it is called Phobetor. Timing solutions give an orbital period of about 98 days, and a semi-major axis of about 0.46 astronomical unit, so Phobetor orbits Lich at a distance slightly smaller than 1/2 of the Earth-Sun separation. The orbit has a small but non-zero eccentricity, with detailed analyses yielding values of roughly 0.02 to 0.03, so that the distance from the neutron star varies modestly between periastron and apastron. The inclination of the orbit relative to the plane of the sky is around 47 to about 50 degrees in dynamical fits that model the mutual gravitational perturbations between Phobetor and the middle planet. These parameters place Phobetor on a nearly circular, moderately inclined orbit that lies in the same general plane as Draugr and Poltergeist, and sits just outside the near 3 to 2 commensurability between the middle and outer planets. At this distance, and for a neutron star mass near 1.5 times the mass of the Sun, the orbital velocity of Phobetor is of order tens of kilometers per second, and the gravitational field of Lich still dominates its dynamics by a wide margin. The mass of Phobetor is inferred from the amplitude of the pulsar's reflex motion, and from the way in which its gravitational influence modifies the orbit of Poltergeist over time. The analysis of non-Keplerian timing residuals with n-body dynamical models yields a true mass for Phobetor of about 3.9 times the mass of the Earth, with uncertainties of a few tenths of an Earth mass. This mass is comparable with that of Poltergeist, and places both planets in the super-Earth regime. interior structure models that relate mass and radius for rocky and partially volatile rich planets suggest that a planet of this mass around a pulsar is likely to have a radius of around 1.5 times the radius of the Earth, with some catalogues listing values between about 1.5 and nearly twice the Earth radius, depending on the assumed composition. Combining a representative radius in this range with the measured mass gives a mean bulk density modestly higher than that of the Earth, consistent with a predominantly rocky composition and possibly a somewhat larger iron core fraction, or a modest contribution from high-pressure ices. The uncertainties in radius and composition remain significant because there is no direct radius measurement for Phobetor, but the mass and density estimates favour a compact mainly solid planet rather than a gas-rich mini-Neptune. In this framework, Phobetor can be described as a super-Earth, whose mass and likely radius point to an interior structure that includes a dense core and a substantial silicate mantle, with any volatile layer limited in total mass compared with a rock. The orbital period and small eccentricity imply that tidal forces between Lich and Phobetor have acted over timescales of at least hundreds of millions of years. Tidal torques remove rotational energy from the planet and tend to align its spin axis and orbital axis while damping eccentricity. For a super-Earth mass planet at about 0.46 astronomical unit, the tidal locking timescale is longer than for the inner planets, but still finite on geological timescales, and for plausible interior dissipation parameters, it is possible that Phobetor has approached a state of slow rotation or partial spin-orbit synchronization. However, the present rotational period and exact obliquity cannot be measured, and models of tidal evolution at these distances retain significant uncertainties. The current low eccentricity shows that tidal effects and disk-driven damping during the early history of the system have already acted to reduce orbital non-circularity, and that present-day tidal heating in the interior is expected to be modest compared with radiogenic heat production. As for the other planets, the radiation and particle environment at the orbit of Phobetor is dominated by Lich's spin-down power and high-energy output. The soft X-ray luminosity of Lich is of order a few times 10 to the 29 ergs per second, and the total spin-down power carried by the relativistic pulsar wind and low-frequency electromagnetic waves is roughly 10 to the 35 ergs per second. At a distance of about 0.46 astronomical unit, the X-ray flux incident on Phobetor is lower than that on Poltergeist, by a factor of about 1.5, and lower than that on Draugr by a factor of nearly 6, but remains higher than the X-ray flux received by Earth from the Sun in typical conditions. The particle wind flux declines with the square of the distance as well, so that Phobetor experiences a reduced but still substantial bombardment by relativistic particles compared with the inner planets. These particles can erode or chemically modify surface materials and can drive atmospheric escape if a gaseous envelope is present. Simple energy-limited escape models applied to planets around neutron stars show that high-energy photons and wind particles can remove light atmospheric components efficiently from low-mass planets at short orbital distances. For a planet with mass of nearly 4 Earth masses and a surface gravity approaching twice that of the Earth retention of heavier molecules is more favourable, and the timescale for losing a dense heavy gas-dominated atmosphere is longer. Whether Phobetor currently has any atmosphere depends on its initial volatile inventory, the composition of the disk from which it formed, the timing and intensity of irradiation, and any magnetic shielding produced by an internal dynamo. None of these factors are directly measured for this system, so the presence or absence of an atmosphere remains an open question. In many models, a super-Earth at several tenths of an astronomical unit from a millisecond pulsar may retain at most a thin residual atmosphere of heavy molecules after long exposure to the pulsar wind and X-ray flux, while lighter constituents are largely lost. The thermal state of Phobetor is commonly characterized by an equilibrium temperature derived from the pulsar's estimated luminosity and the orbital distance under the assumption of a simple radiative balance. Different catalogues quote equilibrium temperatures ranging from values below 200 degrees Kelvin to several hundred degrees, Kelvin reflecting the uncertainties in the intrinsic luminosity of Lich at wavelengths, relevant for planetary heating and the unknown albedo of the planet. These estimates show that the planet's surface is likely to be cold in the absence of strong greenhouse warming, with mean radiative temperatures below the freezing point of water, but they do not capture local temperature variations between the star-facing and night sides or between equatorial and polar regions. If Phobetor has no substantial atmosphere, surface temperatures would respond directly to the pattern of high-energy irradiation and would be set by the balance between incoming radiation, conducted heat from the interior, and thermal re-emission. If a thin or moderate atmosphere exists, wind and circulation patterns would redistribute heat and influence the range of temperatures, but such processes remain hypothetical. The surface and near-surface materials would be subject to continuous high-energy processing by photons and particles, which can darken or brighten mineral surfaces, alter chemical bonds, and produce secondary layers of regolith. The interior structure of Phobetor inferred from super-Earth models likely includes an iron-rich core that contributes a significant fraction of the total mass, surrounded by a silicate mantle that may remain partially convective over long timescales due to radiogenic heat and residual heat from formation. For a planet of this mass, internal pressures in the core and lower mantle are significantly higher than in the Earth, which modifies mineral phases and the equation of state of the interior. If enough conducting liquid exists in the core, convective motions could generate a magnetic field through a dynamo process. The interaction between any such planetary magnetic field and the strong structured magnetic field and particle wind of Lich is not yet constrained observationally, and would require dedicated modelling. Infrared observations of the Lich system do not reveal strong emission from warm dust at radii, comparable with Phobetor's orbit, so there is no evidence for a dense debris disk occupying the same region. This supports the conclusion that Phobetor currently orbits in a relatively clear environment, dominated by the pulsar wind and interstellar medium, rather than by a massive disk of small solids. Within the limits of present observations and models, Phobetor is therefore described as a super-Earth mass planet, on a nearly circular orbit at about 0.46 astronomical unit from Lich, with a likely mainly rocky interior, enhanced surface gravity relative to the Earth, and continuous exposure to a reduced but still strong high-energy environment compared with its inner neighbours. Its outer position and mass comparable to that of Poltergeist complete the known architecture of the Lich planetary system and provide an important example of how multi-planet systems can exist and remain dynamically stable around an old millisecond pulsar.